Welcome to MSB lecture series on main group chemistry. In my previous lecture, I was discussing about silicates and their transformation. Essentially, when one kind of silicate undergoes transformation, it involves breakage of one or more SiO(Si) linkages. So, let me discuss more on silicates in this lecture. Silicate minerals are rock forming minerals and made up of silicate groups. They are in fact the largest and most important class of rock forming minerals. Whatever the minerals we have in the earth crust, these silicate minerals accounts for 90% of them. The basic unit of all silicates is essentially a tetrahedral ion, something like this, Here these four corners of a tetrahedron are occupied by oxygen atoms. At the center silicon is there. So, total charge will be SiO4 4 minus. So, that means O minus, O minus, O minus, O minus here. Okay. These are the basic units of all silicates, whether we have one dimensional, two dimensional or discrete silicates or three dimensional. They consist of this kind of units. Essentially, these silicates are classified based on the structure of their silicate groups, which contain different ratios of silicon and oxygen having SiO(Si) linkages. Okay. So, let us look into the classification of silicates now. We have several type of silicates. Orthosilicates or nesosilicates or island silicates, where we have discrete groups. Pyrosilicates essentially involve having one SiO(Si) linkage, something like this, where we have Si is here one Si and one Si is here, they are linked by one oxygen atom. So, this is essentially pyrosilicate. And then of course, we have cyclosilicates, where two oxygen atoms are linked with the neighboring ones in cyclic fashion or in one dimensional chain fashion. So, when it is chain, they are called inosilicates or chain silicates. And again, among chain silicates we have two type of silicates, single chain silicates and double chain silicates, and also we have sheet silicates, where three oxygen atoms are shared with the neighboring SiO4 tetrahedra, and also we have tectosilicates or frame silicates, in which all four oxygen atoms are sharing with the neighboring ones to give a three dimensional network. So, the corner oxygens are not shared with other in case of orthosilicates, they are discrete, okay, having this kind of independent units. Each tetrahedron is isolated. This group is often referred to as the island silicate group, because it does not have any linkage with neighboring groups. The basic unit, as I mentioned, is again SiO4 4 minus. In this group, the oxygens are shared with octahedral groups that contain other cations such as magnesium, iron or calcium in their divalent states. Olivine is a good example that has composition of MgFe twice SiO4, and you can see here this is a cyclic silicate essentially. So, something like this, if we connect like this, it leads to the formation of a cyclic silicate. On the other hand, it can be something like this. It can continue like this, okay, and one will be that side. So, if you have something like this, this will be a chain silicate, as you can see in depot side, and in the cyclic one, it's we have 1, 2, 3, 4, 5, 6 are there. So, that is essentially another 3 I have to put here. This is an example for beryl, the beryllium ore, as well as this is referred to as emerald. This is essentially a gem. Okay. And then, as I said, if they share two strands, then we will be having chain silicates of this type here, cyclic silicates of this type, and this is an example for asbestos, and here you can see here. And of course, in case of asbestos, what we have is we have some of the silicon atoms replaced by calcium as well as magnesium, and the composition of tremolite is given here. And in case of silicate sheet, this is how it looks like. 3 oxygen atoms, essentially 3 oxygen atoms are here, 1, 2, 3. These oxygen atoms are shared essentially here, so something like this. Okay, so that leads to the formation of a sheet silicate. Example is talc, mica and several clay minerals, and of course talc composition is this one here, Mg3OH twice Si4O10 is the composition of monomeric unit. And when SiO4 tetrahedra shares 3 vertices with adjacent tetrahedra, sheet silicate results with the formula Si4O10. Okay. Si4O10, 4 minus and N. So, this is typically for a sheet silicate composition of monomeric unit. The bonding within the silicate sheet is very strong, but between them is weak. So, the compounds having this kind of can be cleaved into thin sheets, and these thin sheets are held by weak forces. As a result, they slide over other. In talc, for example, we have Mg3 OH twice Si4O10, this is talc. Okay. Here cations only reside between the alternate silicate layers sandwiched between the 2 Si4O10 4 minus sheets with magnesium and OH ions. These metal silicate sandwiches then stack together. The bonding between the sandwiches is weak van der Waals forces. So, talc is very soft, you can see here. So, this is how in one 2 silicate layers are sandwiched okay, with magnesium 2 plus and OH minus ions, and such sandwiched silicates are held together by weak van der Waals forces. So, these forces are so weak they slide over. That is the reason we see it is very smooth. The talc whatever we use is an example for this silicate. Okay. Ortho silicate, you can see how this SiO4 4 minus tetrahedra are spread out without having any OSI linkages. Okay. And pyrosilicates, if one of the corner oxygen is shared. So, this is an example for pyrosilicate here. So, this is an example for pyrosilicate. Of course, pyrophosphate is also there. So, we have only one OSI linkage, and in this case the basic structure unit is, if you can count now 1, 2, 3, 4, 5, 6 and 7. So, that means Si2O7 6 minus will be its composition. A good example of a pyrosilicate is the mineral hemimorphite, having the composition it shown here in this slide. This is essentially Zn4Si2O7 OH and H2O. Some pyrosilicates are a combination of single and double island silicates, as you can see in epidote with this composition shown here. Okay. And of course, this is how the pyrosilicate looks like, having one Si-OSI linkage. Of course, O is tetrahedral here, you can see here. These are the examples for pyrosilicates, you can see here. Okay. And pyrosilicates, of course, 2 such units are bridged by some of the other cationic species, zinc. Okay. Here you can see this is an example, and this is also a precious stone, hemimorphite, this blue in color. Let us look into cyclosilicates. If the 2 oxygen atoms of a tetrahedron are arranged in a cyclic fashion, something like this. Okay. So, this leads to the formation of cyclosilicate. Of course, here you can have 3 6 membered or even 8 membered or even 11 membered you can have. A 6 membered ring forming the structural group of Si6O8 12 minus. 3 membered rings have Si3O9, you can see here 1, 2, 3, you can just see here, okay. 3 plus 6, okay, 3 plus 1, 2, 3 plus 2, 2, 2, 6, it will be 9. So, Si3 O9 6 minus here, and 4 membered rings can also be there. So, something like this. So, you can also have a 4 membered ring. Then you will have Si4 O12 8 minus, and so on and so forth. You can have similarly 5 membered ring also. In these cases, the composition of basic structural unit is SiO3 N that I have shown here, 2N minus. A very good example for this cyclosilicate is the mineral beryl, again B3Al2 Si6O18 beryl. Beryl is also a source of beryllium. That also I showed you how to extract beryllium from beryl while discussing the chemistry of group 2 elements. Okay, so, yes, this is the trimer, this is tetramer, and this is hexameric structure of cyclosilicates. And of course, here you can see the beryl, this is how it looks like, and when we change these cations, we can see different color comes into picture. These are all used in jewelry. And sheet silicates are quite important when we consider minerals such as micas and other things. So, here basically what happens, one or more silicon atoms are replaced by aluminum atom. When you replace one silicon with aluminum atom, in order to balance the charge, one extra cation needs to be added. In these cases, okay, what happens essentially, potassium or magnesium comes into picture. So, these minerals are essentially called as micas. So, when you replace one silicon, there is a deficiency of one cation. So, in that case basically what happens, one element such as sodium, potassium can be added, or one can also add magnesium per 2 silicon atoms. Okay, so, that way that is taken care, the charge balance is taken care. In micas, additional cations K plus in phalgopite or lithium in the lithium ore, lipidolite lie between the. So, these cations will lie between the silicate sheets, and thus they are bonded more strongly by ionic interactions compared to the weak van der Waals forces we come across in talc. The cleavage of mica is still into thin sheets. Okay. So, other important mineral which have the sheet silicate structure are essentially a variety of clay minerals. Quartz is one of the most known and having several thermodynamically stable crystalline form of silica having SiO2 composition. The most important forms of silica include alpha quartz, beta quartz, tridymite, cristobalite, coesite, and stishovite. And also we have network silicate minerals. If an SiO4, if a SiO4 tetrahedra shares all 4 of its vertices, that means here if I consider here, if all these 4 vertices are shared by neighboring SiO4 tetrahedra, so then that results in network silicate minerals. If 3-dimensional network, so here essentially a negative charge is readily introduced into the framework by replacement of some silicon atoms by aluminum atoms. So, in these cases, if you replace one or more silicon atoms, naturally what happens, a negative charge is introduced. So, to compensate that one, basically what happens, some counter cations will be added. So, a commercially important class of network of aluminosilicate is essentially known as zeolite. A large range of both synthetic and natural zeolites are known. One of the basic building blocks for several zeolites is the sodalite cage. I will show you what is sodalite cage is. This is how the sodalite cage looks like. In this one you can notice we have about 1, 2, 3, 4, 5, 6 4-membered rings are there and 8 6-membered rings are there. So, that means essentially each sodalite consists of 6 4-membered rings and 8 6-membered rings, and several synthetic coordination polymers and metal organic frameworks having this kind of structures are known. For example, you can see here 4 such units are linked in this fashion and here. So, in this one we have essentially 8 such units interlinked together, and of course, this is another example that was made in our laboratory. working on copper 1 with bisphosphine, and you can see here the monomeric unit in this reaction of cyclodiphosphazane with copper iodide result in the formation of these cubanes, Cu4X4 cubanes, and these cubanes are shown here and these bisphosphines are shown here. It also consists of 1, 2, 3, 4, 5, 6, 6 4-member rings and 8 6-member rings. This is very similar to the monomeric unit we come across in case of sodalite, and this is a rare and only the example of soft copper 1 and phosphorus 3 ligands leading to the formation of this kind of sodalite network. Okay. Let us look into the chain silicates. If two of the oxygens are shared in a way to make long silicon single chains of linked SiO4 tetrahedra, we get the single chain silicates or inosilicates. And again here the basic structural unit can be seen here, Si2O6 4 minus or SiO3 2 minus. This group is the basis for the pyroxene group of minerals having this composition I have shown here. Having counter cations such as magnesium, iron in this one, or calcium and magnesium along with iron in case of this chain silicate. And of course, this is how the chain silicate looks like. And of course, one can also come across single chain silicates as we see in case of orthopyroxenes. You can see here this is how the clay looks like, the mineral looks like, and the interlinking can be seen from this picture here. Okay. So, if two such chains are linked together so that each tetrahedral group shares 3 oxygen atoms, we can have double chains. The basic structural group being having a composition of SiO4O11 6 minus or Si4O11 6N, and this is the repeating unit. Amphibole group of minerals have this double chain silicate structure. For example, one can look into this one where we have calcium, magnesium and iron along with silicon in this one. Okay. This is how it looks like when two strands are joined together. In between we have a cyclic unit coming into the picture here, you can see here. Okay. So, this again example for double chain silicates, amphibole, and this how these units are interlinked together to give a sheet, and this how one can see how these cations will come and occupy between these sheets getting sandwiched. So, when we talk about framework silicates, again as I mentioned, all the oxygens are shared with another SiO tetrahedron. The basic structural group is essentially SiO2, that means composition of this one is SiO2. Minerals such as quartz, cristobalite and tridymite are based on this structure, and this is how they look like. The arrangement of these can be seen here. Okay. For example, quartz is an ideal example for network silicate. Let us look into the silicones now. Silicones are essentially a group of organosilicon polymers. The complete hydrolysis of SiCl4 gives SiO2, which has a stable 3-dimensional structure, that is we call it as silicates. But instead what we can have is we can have two organic groups and keep two chlorides, and then if you hydrolyze, then we can generate SiO-Si linkages through the elimination or condensation reaction. So, that leads to the formation of silicones. You can see here how it is done. For example, let us take dichlorosilane. This, when it is treated with water, it initially forms hydroxy groups. Okay. So, this one now this reacts with another one. So, it continues. So, here again another molecule can come and it condense and eliminate a molecule of water to give a one dimensional chain. So, this is how silicones are made essentially. So, this organosilicones of general composition R2SiO N are the most important synthetic polymers with a purely inorganic backbone. They are essentially synthesized by hydrolysis of dialkyl silicon dichloride, that is Me2SiCl2 or Et2SiCl2 etc. The monomeric unit Me2SiO, if you consider, is a highly reactive species. In contrast to the carbon analog, silicones have the polymeric structure because Si bond is very highly unstable. As a result, what happens, it leads to the formation of single bond through having this kind of linkages. It goes like this. It continues. Okay. So, depending on the condition we are employing, cyclic silicones can be formed, or it can be chain type silicon polymer also can be formed. Okay. So, and of course, one can also think of branched silicones here, provided we use in between RSiCl2. Simply if we use R2SiCl2, basically what happens, it can give a cyclic or it can give a linear one, and if we incorporate in between RSiCl3, one can think of a branched chain. Branched silicon also we can see. Okay. So, that means essentially we need to have a starting compound such as R2SiCl2 for this kind of polymerization. So, the general method of preparation of such dichloro species in commercial level involves the treatment of Si with 2MECl. So, this is passed over copper heated to 300 degrees centigrade to form Me2SiCl2. So, the commercial production of starting compound for various polymerization involves the reaction of silicon with methyl chloride over heated copper at 300 degrees centigrade. Okay. You can see here. So, this should be converted into through hydrolysis first, like this, and then this one again if you perform condensation, you can generate something like this. It goes like this. Okay. So, here we have R group. So, you can consider, so this one, this essentially gives R2SiO. Okay. So, this is how N comes into picture here. This is the monomeric unit. And here of course, this can also go like this, or if it condenses in a different fashion, one can also think of a cyclic one. This is an R group here. So, either we can have cyclic silicates we can have, or we can have linear silicon polymers of this type. So, hydrolysis of course, it can give a trimeric or tetrameric, and here the whatever the ratio N I showed here, this N depends on the ratio of whatever we are using. Sometime what we can do is we can terminate this one by taking an appropriate combination of R2SiCl2 and R3SiCl. For example, let us consider this one here. So, here so while performing this reaction at some point of time, so for this one what we need is Me2SiCl2 hydrolysis and then condensation. At some point of time for this one, if we add or Me3SiCl, we can terminate it. So, that means that the chain length whatever is there, if I consider this one, okay, this n, the number of the n depends on the ratio of this one as well as this one, and that way one can also perform and grow a polymer of desired chain length. So, silicones are robust materials resistant to high temperatures and hydrolysis, and also find a range of applications including lubricants, sealants, hydraulic oils, cosmetics, car and furniture polishes, medical implants, and also in contact lenses. Okay. So, with this let us proceed to the chemistry of oxides of other group 14 elements. Dioxides of germanium, tin and lead are essentially non-volatile solids. Germanium dioxide closely resembles SiO2 and exists in both quartz as well as rutile forms. It dissolves in concentrated hydrochloric acid forming GeCl6-2 and in alkalis to give germanates. Relatively few open work framework germanates are known, although this is a developing area in recent years. Although silicon and germanium are both group 14 elements, the structural building blocks in silicates are more restricted than those in germanates. Okay. So, larger size of germanium compared to silicon allows it to reside in GeO4 tetrahedra or sometimes GeO4 square based pyramidal or trigonal bipyramidal structure, and of course, GeO6 is also possible, that means having octahedral geometry in environment. Germanium monoxide is prepared by dehydration of the yellow hydrate obtained by reaction of germanium dichloride with aqueous ammonia or by heating germanium hydroxide, which was obtained from essentially hydrolysis of germanium dichloride with water. The monoxide GeO2 is amphoteric, but it is not well characterized as GeO2 and it disproportionates at high temperature. That means, the monoxide is essentially GeO. GeO is amphoteric in nature, but it is not as well characterized as GeO2 and disproportionates at high temperature. For example, I will show you. Okay, so, it gives GeO2 plus germanium and the preparation of Ge5 involves the treatment of GeO2 with lithium oxide. So, this is how one can make some of these germanium oxides, and germanium oxide such as this one having network structure can be seen here. Okay, this composition is here, you can see. Okay. And the other oxides of tin and lead adopt rutile type structure. For example, SnO2 if you consider SnO2 and PbO2, the structures of these are very similar to rutile, that is called TiO2, having octahedral geometry surrounding the central atom. SnO2 occurs naturally as cassiterite, but can easily be prepared by oxidation of tin. The formation of lead oxide requires the action of powerful oxidizing agents such as alkaline hypochlorite on Pb2 plus compounds. On heating PbO2, it decomposes to PbO via a series of other oxides. Let me give how the lead oxide with lead in plus 4 state decomposes to eventually give lead oxide with lead in plus 2 state before I conclude this talk. So, this on heating to 647 Kelvin gives Pb3O4, which eventually gives PbO on heating to 878 Kelvin. Okay. So, this is how you can see. Of course, PbO2 is highly oxidizing in nature to get reduced to Pb2 plus compounds such as PbO. Okay. So, let me discuss the remaining part of group 14 heavier element oxides in my next lecture. Until then, have a pleasant reading of inorganic chemistry. Thank you very much.